Okay, so in this lecture, I'll be talking about the concept of products of groups. Products of groups. So, our goal is primarily to start with, for example, say two groups, say G1 and G2 are two arbitrary groups, and we want to construct a new group using G1 and G2, while sort of we preserve their structures as well. So what we try to do is that so after all they are groups, so obviously they are sets, right? So if they are sets, we can talk about their direct, I mean their Cartesian product. Okay, so let's talk about its Cartesian product. Now we know by definition this should be the collection of elements of the form AB, ordered pair AB, such that A comes from G1 and B comes from G2. Okay, so this is obviously a well-defined set, right? Okay, well-defined set. Okay. Now my question is that can I form a group out of G1 cross G2? That's primarily the question I want to raise. Suppose I choose two elements, say A, B, and C, D, both from, say I consider this group to be G. So I consider two elements from G, and I want to talk about some operation which can be used to compose, say I indicate it by star, so that I can compose these two elements into a new element which is still of the form of an ordered pair, such that it is still considered to be an element of G, right? That is, I want to compose them in such a way that I get an element EF such that E is still in G1 and F is still in G2. Okay. What is the most intuitive operation which I should think of at this moment? Which is, we already know that, suppose let's say G1 and G2 are groups. Let us give some operations to it with respect to, uh, say an additive operation and a multiplicative operation respectively. You can also think these operations to be mere symbols, not specifically an additive operation, as we have, I mean to say this addition is just a symbolic notation for an additive operation. Not I do not primarily mean it to be the, algebraic addition or the arithmetical addition, which we have been talking about in a junior classes. Okay, so we impose two simple operations on G1 and G2 for them to be a structured group. So then we know that A plus C will again be in G1 and B plus D, sorry, B and D are elements from G2, right? So B dot D will be in G2. So if I want to compose these two ordered pairs A, B and C, D such that the resultant element is also an ordered pair with the first element coming from G1 and the second element coming from G2, our primary intuition must be that we compose them, and this is obviously the definition of the operation which I want to talk about, is by just component wise operation which preserves the operation of each group. So since A and C comes from G1, we compose them using the operation on G1, and since B and D, sorry, I have C here, and since B and D come from G2, so I compose them using the operation on G2, right? Then observe that A plus C by closure of G1, it's an element of G1, and B dot D by closure of G2, it's an element of G2. So this is again an element of G, right? Okay. Now, uh, uh, observe that this operation is also associative by nature, and that comes direct, right? Because suppose I choose A, B, C, D, and E, F, and I do this first, then I would be getting A, B star. So this will primarily be C plus E D dot F, and then so I'll get A plus C plus E, right? And B dot D dot, right? This is what I would get. Okay, clear? But then I know that this additive operation and this multiplicative operation both are group operations, hence they are associative as well. So if they are associative, then I can write this as A plus C plus E and B dot D and F. So a mere backward calculation just speaks that this is exactly equal to first doing A, B with C, D, and then doing E, F, E, E, F, right? This is clearly a well-defined operation. Okay. Hence, this operation is associative in nature. What can I say about the identity element? Suppose, um, we consider suppose 1G and 1G1 and 1G2 are the identities on, sorry, in G1 and G2. Then if I consider the ordered pair, okay, let me be a bit more precise because I am considering the additive and the multiplicative operations. So I should talk about say 0 and 1, right? I can precisely talk about the identities in G1 and G2 by symbols 0 and 1 because I have used the symbol of addition and multiplication to denote the operations on G1 and G2. So if I consider the element 0 1, the ordered pair 0 1, and I compose this with any element of the form AB, then I should get A 0 plus A and 1 dot B, but that exactly AB. And you can observe that this happens similarly if I do AB dot I mean AB composed with 0 1, right? This would be same as AB composed with 0 1, right? And hence, since 0 and 1 are the unique identity elements in G1 and G2, hence this should be the unique identity element in G, right? So there is also an existence of identity. I guess now it's clear that we can also talk about inverses, because if I consider the suppose A and B, I choose an element A and B from G, and I consider this ordered pair minus A and B inverse, right? So minus A is trivially the additive inverse of the element A from G1, and B inverse is the multiplicative inverse of G from of B from G. Then if I compose this up with AB, then we know that I should get minus A plus A, and you have here B inverse dot B, and that's exactly 0 1. So this will indeed happen from the other side as well, right? So therefore there is also an inverse in this. So what we conclude is basically that G with respect to this operation is a group, right? So what are we exactly doing is we are constructing the Cartesian product of two given groups, and we are using an operation on it such that we have a component wise composition preserving the operations of each group. That's what exactly what we are doing. Okay. Now clearly enough, if we talk about a finite number of groups, then also all these definitions hold, right? Because we actually are not concerned about what number of groups we are using for the Cartesian product. We just require each components of the tuple we will be talking about, and that's enough, right? So clearly we can talk about we can talk about I should say it like this: G1 cross G2 cross and so on and so forth till Gn. I'm not talking about the operations of each individual group anymore because that's not quite specifically needed here, right? So if I choose it to be G, then G is again a group. Then G is a group by component wise operation which preserves the operation of each group, which preserves the operation on each group. Right? Clear? Well, I'm coming in a second. Okay. So yeah. So this is what we call an external direct product of n groups. Okay. So this is defined as, so let me just give the definition. Uh, the above group, that is, I am specifically talking about this group, is called an external direct product. An external direct product of the groups G1 till Gn with respect to above defined operation, right? Above defined operation. Okay. So therefore, if we have a collection, a finite collection of groups, then we can talk about an external direct product of them, which precisely gives rise to another group, right? For example, if I talk about, say, R as a group, let G be is equals to R, then I can talk about, let's say let Gi be is equals to R, then I can talk about the product. So this is often the symbol we use for denoting the direct products. So we are sort of using the product Gi n times, right? So I'm trying to say this, which is basically G1 cross G2 and so on till Gn. Each Gi is R, so this is basically R cross till R, which is n times we're doing it. So we get simply Rn, and the elements of Rn are precisely the n tuples, n real tuples. So we know that R is an additive group, right? So if I choose any n tuple, so if I choose n tuple I is equals to 1 to n ai, then I choose bi, I is equals to 1 to n, then I can get ai plus bi, I is equals to 1 to n, I is equals to 1 to n to be the tuple ai plus bi, I is equals to 1 to n, right? So these are merely some easy observations. There is nothing too complicated to talk about these. Um, okay, let us consider one more example. This is sort of not that much non-trivial, but it will help us understand that why the way we were using the preservation of operations. So suppose I choose G1 to be Z, G2 to be let's say S3, and G3 to be the general linear group uh, with elements from R and of order 2 or dimension 2 cross 2. Okay. So if I consider G to be G1 cross G2 cross G3, then an element from G will merely be of the form is such that, so we choose an element, A, let's say A from Z, then we have an element sigma, let's say from S3, which is a simple permutation of the elements 1, 2, and 3, and we get a matrix, right? A, B, C, and D, and the restriction on this matrix is that AD minus BC is non-zero, right? because we are talking about matrices with a determinant non-zero. Clearly, we want to talk about the multiplicative group of matrices. That's exactly what we are going to talk about. So yeah, that's it. Now, so suppose I choose another element. Let's say y comes from G is such that y can be written as say B, say gamma, and say we have here P, Q, R, and S, right? Then what is the composition of X and Y? So it should be basically A plus B because 0 is an additive group. S3 comes with the composition of maps, and G3 comes with the product of matrices, right? Times P, Q, R, S, right? So this is what we get. I hope this part is clear. Now we can also extend the concept of direct products to infinitely many groups as well, because again, while we introduced the concept, there was no restriction to the number of groups we will be talking about because the operations which we are concerned are basically component wise. So we can also talk about um, we can also talk about you know infinite, or I should say countably infinite uh, direct products, right? Direct products where the tuples can be thought of as sequences, nothing else, right? Sequences. You can think of it like that. What I'm trying to say is that I consider groups from I is equals to 1 to infinity, and if I choose an element, say x from here, then x is simply a sequence of elements, say 1 to infinity, where each ai comes from each ai. That's it. That's what I'm specifically talking about. And the operation is exactly same, right? We have a component wise composition preserving the operations of each group. In fact, we can also talk about direct products of an arbitrary collection of groups as well. For example, suppose let's say F is an arbitrary collection of groups, say Gi, such that I belongs to some indexing set I. Then we can also talk about the direct product of groups uh, of the arbitrary direct product of groups. And since we technically have no idea of how an element should look like, because when we are talking about a countable collection, be it finite or infinite, then we can distinctly identify each element of the group in order to construct out the the ordered pair, or the ordered tuple. But in this case we are just talking about an arbitrary family of groups. So merely we do not have a strict structure of the elements of gi, and so just what we try to denote it as is pi of a, we can talk about, or pi of ai, specifically I comes from capital I, and pi of bi with I coming from capital I. These are the elements notations, or at least notations of elements from gi. And the operation which we can talk about is that I just compose them component wise, where each component is merely just these ais or these bis, right? So this is just product I is equals to I in I, ai, right? That's it. So what we are trying to do is that we are just using the multiplicative notation for each root. That's what I want to talk about. Similarly, if I want to talk about the identity elements, I can then just construct the collection like this with each element coming from the identities of gi. So I can just consider the collection 1 of gi, where I comes from capital A. That's it. If I talk about the inverse element of some element, say A, then I can talk about the product of A I inverses, where I comes from capital A. So analogous construction, right? There's nothing too complicated here. Uh, Now, in case of an infinite direct product, at least an countably infinite direct product, we can in fact restrict that to finitely many non-identity elements. What I'm trying to say is that uh, you know uh, see, what I'm trying to say is that suppose, I can consider, say this. Okay, okay, we consider a countably infinite direct product of groups in such a way that the elements in GI, say pi ai, I is equals to 1 to infinity from GI, is such that all AIs equals to 1 except for a finite number of AIs. Okay, except for a finite number of AIs. Okay. So this structure is often called a restricted direct product, and I guess it's also called a direct sum. It's also called a direct sum. So we are considering only finitely many non-identity elements. If I consider all the elements to be arbitrary, like we have a strict structure to the elements of the countably infinite direct product. So if all the elements are specifically non-identity, at least if I talk about infinite elements being, non-identity, then there's nothing to, useful to talk about. But rather this one can be, imagined in a bit different way, where we talk about the elements from a countably infinite direct product where only a finite number of elements are non-identity and rest all of the elements are identity. So operating with such a direct product is merely, easier than talking about the normal countably infinite direct product. So this is often called the restricted direct product, or often, I guess, also often called the direct sum. Whatever. Uh, the next obvious question which should arise is that what can I say about the order of a direct product? Now I'll merely be talking about finite direct products. Okay, if in any case we talk about infinite direct products, or if in any case we don't require it being finite or infinite, that's something, else. But specifically we will be focusing more on finite direct products. So what is the order of a direct product? Okay. Now this is a merely simple answer, because we know that if I talk about G1 cross G2 and so on till Gn, then we know that the order of this is merely the order of each of the groups, and then we multiply it out, right? So simply the order of a direct product is the product of order of each group, right? Okay. The next question which I would obviously want to answer is that we are starting with an arbitrary collection of groups, say a finite collection of groups, but still the collection is arbitrary because there is no fixed order specified for the groups we should pick, right? What I'm trying to say is that we are given n groups, say G1, G2, G3, and so on. Now we have already structurized the direct product G as G1 cross G2 and so on till Gn, right? But my question is that suppose I consider G to be some, say G3 cross G4 cross G2 cross G1 cross Gi cross Gn cross Gi minus 1 and so on, right? So what I'm trying to do is that I am just forming this direct product out of the same collection, but I have a new arrangement of these groups. So my question is that are these structures similar or equivalent as groups? Okay. So are these structures equivalent? And whenever I say equivalent, I mean equivalent by groups, equivalent as groups. Okay. Now, intuitively, this must be clear because since we are talking about component-wise operation, there should it specifically need not make any difference to the group structure, right? But if I talk about equivalence as group structure, then the thing which I should mathematically talk about is an isomorphism between them, which I can surely talk about. Suppose I consider this collection. See, what are the only things which, by rearrangement, what are the only things which specifically makes a difference in the structure of the collection? These are the indices, right? So if in any way we can fix out these indices, then I can talk about the isomorphism between them, right? So what I'm trying to do is that I am considering the direct product I is equals to 1 to n, and I'm thinking of these indices I to be the image of some arbitrary element, some arbitrary positive integer from 1 to n under some permutation. Because see, suppose I talk about in this case, suppose this example, if I talk about, okay, then observe that I can consider a permutation which maps 1 to 3, 2 to 4, and then something to 2, something to 1 here, n goes back to, say, let's say I, then let's say I plus 1 goes to n, and so on and so forth. That's what I'm trying to talk about, right? I can consider a permutation of the indices, and I can talk about a rearrangement. I guess now it's clear. So what I'm trying to do is that I am considering a map phi from G1 cross G2 cross till Gn to um, some rearrangement, say I'm using the indices later, some rearrangement. Now, what am I specifically trying to do here is that I am thinking of these indices 1, 2, and n to be the image of the indices of the rearrangement of these groups under some permutation. Under some permutation. Let that permutation be pi. Let that permutation be pi. So I am thinking of 1 being the image of, sorry, the pre-image of some permutation. So I am mapping, say I map 1 to some a when a belongs to block n. Block n means the collection of elements from 1 to n. Okay. So under pi, under pi. So if so 1 can be corresponded to pi of a, right? Or I can write a as pi inverse of 1. That is what I want to talk about. So I can just I can just denote the rearrangement corresponding to the group G1 to be pi inverse of 1. Similarly, I can talk about this to be pi inverse of 2, so on and so forth. I can talk about this to be pi inverse of n. So this just primarily gives us a rearrangement, right? And how do we map this out? So we just are talking about some changes in the indices. So therefore pi of any element, say G1 till Gn, gets mapped to so G of pi inverse 1, G of pi inverse 2, and so on and so forth till G of pi inverse n, right? But observe that this is merely just an isomorphism. This is just an isomorphism. Because this isomorphism specifically comes out from the simplest fact that we are talking only about components, right? We are talking only about components. So if I talk about the kernel of this, see, this is obviously a homomorphism, because since we are just talking, the operation will happen component wise. So if it gets distributed on the left hand side, it will also get distributed on the right hand side. So homomorphism is trivially understood. In fact, surjectiveness is also trivially understood, because whatever element you choose from the right hand side group, you can always get an element from the left hand side such that the indices are related like this. That's it, right? That's exactly, surjectiveness is pretty obvious out from here. Oneness is also, injectiveness is also pretty obvious, because if I consider the kernel of this homomorphism, then I need every element G1 till Gn to be mapped to 0, right? Yeah, that's precisely what an element out from a homomorphism is, right? I want to map every coordinate to 0. But if I want to map every coordinate to 0, every coordinate on the right hand side will also get mapped to 0, because if the left hand n tuple gets mapped to 0 with every component being 0, the right hand side element, it just consists of the same elements just with a rearrangement, right? So it makes no difference when all the elements are 0. Hence the kernel must be the only element in the kernel must be the 0 map. Yeah, I mean the 0 element, right? Right? see, let me just speak this out. This is very trivial because if I choose an element, say G1, G2 till Gn from kernel of phi pi, then G1, G2 till Gn must gets mapped to say identity, right? I was talking about 0, but that's quite obvious, right? So I talk about 0 or I talk about 1 makes no sense because whenever I talk about 0, I seem it to be an additive group. Yeah, so I was studying vector spaces, so the zeroth element just came to my mind. So let's not confuse this out. But then G pi inverse of 1 till G pi inverse of n, this must get mapped to identity. But obviously we are talking about n tuples, so we have an equality which must be, so this should be equal to, sorry, this should be equal to the collection of all identities as n tuples. So therefore we have a coordinate wise comparison which speaks that every element G pi inverse I is equals to 1 for all I, but that specifically means each of these elements are identities. Therefore the only element in the kernel is the identity element, and hence this is injective, right? So this is obviously an isomorphism. I hope this part is clear. Okay. So now what we actually want to do is that we want to establish a correspondence. Okay. So our goal is to establish a correspondence between the GIs and direct product of these GIs. Okay. Like now, why do we want to do that? Because this is coming from a very trivial example of suppose I choose R3. Suppose I choose R3. I know R3 is the direct product of R with itself thrice, right? So suppose this is the x-axis, right? So this x-axis is nothing but R itself, right? So this group R, it merely sits inside R3 as a subgroup, right? The x-axis obviously forms a subgroup in R3, right? Individually, independently. Because any element you, any two elements you choose out of R3, the negative of each of the elements are also in R3 and their composition will also be in R3 because its y coordinate and z coordinate will still be 0 if you add them out, right? Similarly for y and similarly for z axis, right? They individually can be considered as a subgroup. So each of these components, they sit inside R3 as a subgroup, right? So this is one one sort of observation. Another observation is that if I choose any element out of R3, suppose I choose an element, say here alpha, say alpha is of the form x1, y1, z1. What I can do is that I can project alpha to be an element of R, supposedly let's say the x-axis, when we only talk about its x coordinate, right? So in a way, if I try to generalize out this fact, I can say that if I am given a direct product, then I can talk about each of the elements in the direct products to be projected to the respective components, to the respective components, because x1 can be thought of as an element on the x-axis corresponding to its coordinate in the x-axis, in accordance with the x-axis. Similarly, if I talk about each component, then I can consider them to be sort of a subgroup sitting inside its direct product. So that's what I want to talk about in the next theorem. So theorem, let G1, G2 till Gn be groups and let G be the direct product of these groups. Okay. Then number one, for all fixed I, the set of elements of G which have identity of Gj for all j not equal to I in the jth positions, and an arbitrary element from Gi at the ith position is a subgroup of G, which is isomorphic to Gi. That is what I want to speak about, is that Gi is isomorphic to the collection of elements of the form 1. All the elements are 1 except Gi. Gi can also be 1, but we are talking about arbitrary elements at the ith position, such that Gi is an element of capital G, right? So can you relate this out with what I was talking about there? There was a slight abuse of notation which I used while I was explaining the example. Let me just talk about that to make it clear. When I am projecting this element to the x-axis, I have not used the coordinate expression of it, but I am just simply talking about its x coordinate, that I am trying to suppress this vector alpha to the x-axis. So what should be its coordinate looking like? It should be looking like x1, 0 and 0. Like here the identity elements are 0 because R3 is an additive. I guess now you can understand what this first statement of this theorem speaks, right? And we had already explained in the example that each component seems to be a subgroup. Okay, so by isomorphism, right? Since I have said that this collection of element is isomorphic to Gi, so by isomorphism, Gi, kind of sits inside G as a subgroup, right? So Gi can be identified as a subgroup of G, right? Also, Gi will come out to be normal in G, and since we have a normal subgroup, our mere habit should be talking about its quotient group. So what should be G mod Gi? Now, how do we usually construct a quotient group? So when we're talking about quotient group, we just try to suppress the denominator of the quotient group to identity. That is, we do not want to talk about what we have in the denominator. So merely this should be isomorphic to G1 cross G2 cross Gi minus 1 cross. We don't want to talk about Gi, so we have Gi plus 1 and so on till Gn. Now I guess you can obviously relate this to what we do in case of integers, right? Like if I have some integer G to be n1 times n2 till ni till nr, then what is G by ni? So it's n1 times n2 so on till ni minus 1, ni plus 1 till nr, right? So I guess you people can relate this out. Clear? Okay, so this is the first statement of the theorem. Okay, and it's very easy to prove by the the example I just showed. Number 2 is that for all I, we define pi I to be a map from G to Gi such that what does pi I does is that it extracts out the element in the ith position from each n tuple of G. So G1 till Gn gets mapped to Gi. Okay, this was also what we are talking about in the case of the the example, right? right? So what we are trying to do is that let's go back to the example. What we are trying to do is that we are talking about the x1 and we are extracting out the first element x1, right? Thinking it to be an element from the x-axis itself, right? Sort of what we are trying to do is that we are sort of trying to project it out, project it to one dimensional axis. That's what we are trying to do in R3. So in this case, what we are trying to do is that basically we have if you want to relate this with R3, you can do it obviously by the example I just provided. What we are trying to do is that we are trying to project the direct product onto some component of it. Okay. Then pi I is surjective. Then pi I is surjective, which is obviously obvious. I mean, sorry, that was a horrible statement. So pi I is surjective. And what is the kernel of pi I? So the kernel of pi I, if so, we want to make gi to be 0. That's it, or 1. Let's say 1 because we are going with multiplicative operation. So let it be 1. So kernel of pi I will be collection of all the elements of the form g1. So you have gi minus 1, then you have a 1, then you have gi plus 1, and so on till gi, such that each gi comes from capital Gi. Let's use gj here because we have already used I. I guess this part is clear. And let me be precisely, j is not equal to I. Correct. J is not equal to I. But observe that again, this is simply isomorphic to G1 cross G2 cross Gi minus 1 cross Gi plus 1 and so on till Gn. Right? Because to establish this isomorphism, what we actually need to do is that we just need to talk about elements, small g1 corresponding to capital G1, small g2 corresponding to capital capital G2. The element 1 did not make any difference because that's simply the identity. And the third statement is that's quite trivial, that if x is in Gi, y is in Gj, then xy is equals to yx for all I not equal to j. Okay, clear? So what should be the mere proof of what I want to say here? So proof number 1. So what should be the map be from Gi to to establish this see, the concept of subgroup is merely obvious, right? The concept of subgroup is merely obvious. What I try to do is that I just map Gi to the element we were talking about. Okay. Then you can observe that Gi is obviously an isomorphism because it's obviously surjective. If you start with this element, then you can obviously have a Gi which gets mapped to this element. You can talk about it being 1 1 because if I want Gi to get mapped to capital 1, then this whole element must get mapped to capital 1. So by component wise comparison, Gi must also be capital 1. So the only element in the kernel must be capital. I mean must be 1, right? This is an homomorphism, obviously, because on the left hand side you just arbitrarily compose two elements. On the right hand side you have a composition component wise. Then the ith element will get composed with itself, right? So you can just distribute that out. So it's merely a homomorphism. You can justify that this is an isomorphism. This is a mere justification. Isomorphism justified. Clear? Okay. Now, suppose I choose a map phi from G to G1 cross G2 cross Gi minus 1 cross Gi plus 1, so on and so forth till Gn, right? You can obviously check that when we are talking about this group capital Gi, yeah, this group capital Gi. Now we have already shown that it's isomorphic to this group. So talking about the elements in Gi, we can talk about the elements of the form like this. You can obviously check that this is indeed a normal subgroup, but we can also show this in some other way around, because if I consider this map, such that let's say G1, G2 till Gn, this gets mapped to elements component wise, just leaving the element in the ith position, because we do not have the ith position component here. So we have gi minus 1, gi plus 1, and so on and so forth till gn, right, by phi. So what should be the kernel of phi? So by definition, it should be it should be the collection of n tuples such that this n tuple must get mapped to identity, right? So therefore, if this element gets mapped to identity, that means this g1, g2 till gi minus 1, gi plus 1 till gn, this must be equal to the identity, and there are n minus 1 identities here, obviously, because there are n minus 1 coordinates here. So this implies that gj must be equals to 1 for all j not equals to I, right? Because each of these elements must be equal to 1 and ith element is not there. Clearly, if every gj is equals to 1, then this element must be of the form 1, 1 till the ith element, which must be arbitrary because we have no restriction on the ith element, and the rest of all the elements are 1, right? So you have gn here, but this is exactly gi considered as the subgroup which we spoke about here, right? So this implies by the first isomorphism theorem, G mod gi is isomorphic to g1 cross till gi minus 1, gi plus 1 till g, right? This was merely a easy calculation. Moreover, since we got that gi to be a kernel of some homomorphism, previously while studying homomorphisms and factor groups or normal subgroups, we had seen that kernel is always a normal subgroup. Hence, gi is a normal subgroup, being a kernel of a homomorphism. Okay. The next proof is immediate, right? We skip the next proof, which is surely immediate, because while stating the theorem, I just said that pi I is, by definition it's surjective, and kernel of pi I also comes out by definition. You can just merely follow out from what I said now, right? That's exactly that's very trivial. And the isomorphism you can just establish by coordinate wise mapping, right? You can just map g1 to capital G1, g2 to capital G2, gi minus 1 to capital gi minus 1, gi plus 1 to capital gi plus 1. We are leaving the element which is 1, which is in the ith position. You go on map till small gn to capital Gn, then you will get a isomorphism, right? Okay. The third statement is also quite obvious, but let me just make you understand this. So I am choosing x from gi, y from capital Gj, where I is not equal to j. Now gi and gj can be considered as subgroups of capital G. So I can consider x to be the element 1, 1 with the ith position element arbitrarily chosen from capital Gi, 1 here. Y can be thought of 1, 1. In the ith position is also has 1. In the jth position it has an arbitrary element gj, and you have 1 here where I is not equal to j. But then if you map xy, then the one element gets composed with itself. The ith position you have gi composed with 1 because I is not equal to j. So simply have gi. In the jth position you have the same 1 composed with gj, right? So you have gj, and then you have 1 here. But it makes no difference if I multiply a y first and then x, right? So you have a multiplication of this form. If I just merely talk about, you have a multiplication of the form 1a times b1. That's it. That's what I'm talking about here. Clear? Okay. So okay, this map g1 cross g2 till gn, mapping it to gi, which was stated in the theorem. This is called the canonical projection, or you can simply call it a projection map. Okay. While gi getting mapped to G1 till Gn, just as we stated in theorem 1, that's called a coordinate map. That's called a coordinate map. Let me just explain the literal sense, which I have already explained while I was giving the example, that we are considering the collection of all the components as direct product, and we are sort of trying to consider each element and project it out onto any one of the components, right? So that's why the term canonical projection or simply projection. And in the second case, we are choosing a single component, a single element from capital Gi, say small gi, and we are considering it to be an element of a tuple. Now, elements of tuple primarily forms, a coordinate in an n-dimensional space if you think of vector spaces or if you think of R. So it merely corresponds to some coordinate, right? In a very structural sense. So if we are considering an element Gi and we are mapping it to an n tuple, so merely we are forming a coordinate out of Gi, and hence the concept of a coordinate map, right? Okay, so yeah, that's quite some obvious uh, you know observations. Let me talk about some more observations. See, there is something more, but what we primarily call an you know internal direct product, okay, which we primarily call an internal direct product. Internal direct product. So in this case, what we do is that we start with a group and we consider normal maps from G, H and K. Then we use the product of them, which is basically of the form HK, such that H from some capital H, K comes from capital K, and we choose these normal subgroups such that they have a trivial intersection. Okay. Then this collection HK, this we primarily write it as like I guess like this. G is H, K. This is called the internal product. This is called the internal product. And this internal product is isomorphic to H and C. H and K are subgroups of G, so we can think of them being groups independently. So if I think of them being groups independently, I can think of the direct product of them. I can think of the direct product of them, and these two are isomorphic. Try to establish an isomorphism, because this is quite a trivial observation. See, if I talk about elements from out of H cross K, so there should be element of the form HK. Okay, map it to the product HK and try to establish an isomorphism out of it. Make use of the fact that they have a trivial intersection. Okay, clear? Okay. So actually what we try to say is that so there are specifically two types of product subgroups. One is the internal direct product, where we start up with a group, we consider its normal subgroups, we multiply them out we multiply them out element wise. Okay, we are multiplying them out element wise, and the chosen groups are mutually they intersect mutually, or they intersect pairwise trivially only in the identity element. Then we get our group structure, which is called the internal direct product. And the external direct product is that we consider arbitrary collection of groups, say finite collection of groups. We consider the Cartesian product of them, and then we induce an operation component wise. This gives an external direct product. What we try to do is that we try to establish a correspondence between an external direct product and an internal direct product, so that there arises no confusion whenever we want to structureize products of groups. Like if we have two different terminologies related to products of groups, then it merely gives us a confusion that what sort of a structure are we trying to deal with. Is are we trying to deal with a product of groups where each component is some subgroup, or we are talking about product of groups where each component are independent in nature as groups. So if we establish a correspondence between an internal direct product and an external direct product, considering groups, they may or may not be subgroups of any higher group, or at least we don't need to talk about them being subgroups or being groups independently, but we can efficiently talk about their products. be it by taking their their Cartesian product and inducing a operation component wise, or taking their product element wise when they have a non-empty, when they have a trivial intersection. That's mainly what we try to do here. In some later lecture, I might be talking about, I think I may be talking about internal direct products, but I don't think there is talking about internal direct products separately, because I've already seen that we have a correspondence between internal and external direct products. So talking about external direct product suffices, or talking about Cartesian product of groups and taking operation component wise, it suffices, right? Talk about product of groups, right? So if I talk about some more properties, there are very, I'll talk about just simply one property because it's already a 1 hour long lecture. The essence of direct product we will see when we will be studying the finite abelian groups. Okay, the fundamental theorem of finite abelian groups are, that is the classification theorems of finite abelian groups, where given some order of a finite abelian group, I can give out all the possible structures which that group might inherit as direct products of other elementary groups. Okay. So the only thing I would want to talk about is that the order of an element in a direct product of a finite number of finite groups, is the LCM of the order of each of the components or each of the coordinates. What I'm trying to say here is that the order of the element G1 till Gn is the LCM of the order of G1 till order of Gn. Okay, that's what I want to say. Now this observation, I guess it should be also trivial, because suppose L is the LCM of these elements, order of G1 till order of Gn. Okay. Okay. Then if I raise the component, the n tuple to L, then so we are just multiplying these L times. So by component by wise operation, this must be G1 to the power L until Gn to the power L. Now order of Gi divides L, because L is the LCM. We know that, so that means that L is order of Gi times some element Q. Hence Gi, therefore Gi raised to the power L must be identity, right? These are specific observations from order. So that means this is just identity, right? Clear? So L has a possibility of being an order of this n tuple. What if we choose an order which is less than L? Suppose I choose, let D be less than L, such that G1 till Gn to the power D is 1. But that implies Gi to the power D is 1 for all I. But that implies order of Gi divides D for all I. But that implies D is a common multiple of these Gi's, right? Right? But we know by definition L is the least common multiple. So that means L must divide D as well. Therefore, it contradicts the fact that D is less than L. Therefore, the least possible element such that G1 till Gn, this n tuple raised to its power is 1, is just L, right? Therefore, order of G1 till Gn is just L, right? Clear? Okay. So what an immediate corollary to this, which is worth mentioning, an immediate corollary. So this is that an external direct product G1 till Gn of finite cyclic groups, finite cyclic groups is cyclic if and only if the order of Gi and the order of Gj is 1 for all I not equal to j. Try and justify this out using the theorem I just said. Okay. Uh, in the next few lectures, I'll be talking about some important notions of class equation. I will be talking about some important notions of class equation. And then we will be entering the concept of finite abelian groups. And there we will see that, or you can also merely follow this up from this corollary, that Zm direct product Zn is isomorphic to Zmn if and only if M and N are coprime. Okay. Whatever, we will talk about this when we start finite abelian groups. Okay, so let this be this much. In the next lecture, we will be talking about class equations. Okay, so meet you guys in the next lecture.